Okay, so consider the curve given by x squared plus 3xy plus 25y squared equals 91. Find all horizontal tangent lines. Find all vertical tangent lines. So here's another question. Who has actually started on the homework that is due this Friday that you're going to be working on recitation? Who has even looked at it? Last week we talked about I would give it to you guys early so you can look at it and have the recitation kind of be a lot better. And it's been available since Saturday. Okay, so you do have some people. Okay. If you're stuck on number 1, go to number 2. Okay, so how do we actually go about doing this? So especially if you actually already looked at the homework problem number 1 is very similar to this problem. So implicit differentiation, okay, we're definitely going to need the derivative. We're going to need dy dx for both parts, right? Because both parts are asking about horizontal, or sorry, they're both asking about tangent lines. So let's actually get that out of the way first, okay, right? We need dy dx for both parts. Okay, so using implicit differentiation. So who wants to be the brave one and tell me what is the derivative of the left-hand side of the equation? Just give me the whole thing. I know you just saw it a minute ago, but this is something you should be able to do, quickly, right? Derivatives is something, it's a basic skill we should all have. It'd also be great to hear from the people who are not on camera. You guys are also taking this class.
I could go.
Who's talking? Hirsch. Oh, it doesn't matter. Yana beat you to the punch.
Okay, so
Oh, Yana just beat you. She says 2x plus 3y plus 3x dy dx, except she is missing something. What's the derivative of 25y squared? Hirsch, you want to give me the derivative of that last term?
Would that be 50y dy dx?
50y dy dx, okay, equals 0. All right, and now we do some algebra to solve for dy dx, right? So we get here negative 2x plus 3y all over 3x plus 50y. Okay, so now I have my derivative. We're going to now use this for the 2 separate parts, finding horizontal tangent lines, finding vertical tangent lines. So how do we go about finding the horizontal tangent lines? Set the numerator equal to 0. Set equal to 0. Okay, so we're going to set the derivative equal to 0. I do want to actually point out here, I didn't really need to solve for dy dx. I could have just not done that. I could have just used this equation and putting dy dx equals 0. I could have just done that in that equation, and then I get what I want, right? That's the same thing, numerator equals 0. So I'll just kind of point that out. I didn't really need to solve for dy dx, but whatever, we did. Okay, so horizontal tangent line is dy dx equals 0. You have dy dx equals 0 for any horizontal tangent line. Okay, so I get 2x plus 3y equals 0. If you want to say solve for y, it doesn't really matter what you do here. So I get y equals negative 2/3 x. Okay, fine. So I did what you told me. I set the derivative equal to 0, and I somehow solved this equation. I mean, you can't really, you can't really solve this equation. I mean, setting this equal to 0, there's two variables in this equation, x and y. There's no such thing as solving this equation. I mean, you can rearrange it. You can solve for one variable in terms of the other, but there's no such thing as, oh, the solution is x equals this, y equals this, right? So what else is going on here? What else do we have to do? A system? What do you mean by that, Jacqueline? With the denominator? I don't know what you mean by system with the denominator. It should equal 0. So you want both the numerator and the denominator equal to 0? Oh, I don't like that. Because if both numerator and denominator equal to 0, wouldn't that give me that the derivative is 0 over 0, which could really end up being any sort of slope? I don't want both numerator and denominator equal to 0. I really don't want that. In fact, I really want numerator equal to 0 and denominator not equal to 0. I don't want to set the denominator equal to 0. That's not correct for this. Any other thoughts? There was a homework question on this, and 3.8 homework was due last week. There was a question that asked you to find all horizontal tangent lines and all vertical tangent lines for a certain curve. Now, did a lot of you just look at another example and then reverse engineer the problem, or did you actually try to solve the problem yourself and understand what the solution meant if you didn't know how to do it? What if you substituted the y into the equation? What if we substitute it? Should you substitute y for negative 2/3 x back into the original? That's probably a good idea, right? What's really going on here is the point that we are looking for has an x coordinate and a y coordinate, right? There's an unknown coordinate out there, right? That's the point of tangency. Okay. I'm trying to solve for two variables at once. I need to find the x coordinate of this point, and I need to find the y coordinate of the point. I have one equation that this point must satisfy, right? The point must satisfy the original equation because the point lies on the curve, right? So x and y satisfy the original equation. However, x and y also satisfy the equation y equals negative 2/3 x. Why? Because that equation is equivalent to saying that the slope is equal to 0. So we have two equations, simultaneous equations, that x and y must satisfy. Now, this is actually no different from a non-implicit problem. Although a non-implicit problem, it's not quite as obvious. In a non-implicit problem, you have something like, oh, y equals, let's say, x cubed minus x. And I want to find the horizontal tangent lines. So I have 3x squared minus 1 equals 0. So you're searching for a point of tangency whose x coordinates and y coordinate satisfy this system of equations. But we don't really think about it that way. We kind of just solve for x from the second equation and plug x back into the first, right? But it really is a system of equations. The difference with the implicit problem is that both equations have both x and y in them. Like there's no way to kind of separate them out, right? The derivative in a normal problem has only x, but here the derivative has both x and y. But it still comes down to solving a system of equations. You're solving y equals, you're solving the original equation that tells you points on the curve, and you're solving the equation that tells you the derivative equals 0. So it comes down to the same exact principle. So let's make a note of that and then actually do the algebra. So let's call this equation 1. The unknown point of tangency satisfies the original equation, right? Because it lies on the curve. Because it lies on the curve. And equation 1 because dy dx equals 0. So I have two equations. So I'm going to substitute equation 1 back into the original. I'm going to put y equals negative 2/3 x back into the original equation. Right, and then I solve for x. Okay, so what do we get here? We get x squared minus 2x squared plus 100 over 9. X squared equals 91. 91 squared over 9 equals 91. So we get two solutions. We get x equals negative 3 or x equals 3. And then what is the y value? Remember the y value, remember that y equals negative 2/3 x. So we get y equals 2 or y equals negative 2. Nicole has a question. Would we do the same thing if we had to solve for a slope that was a different value? Well, if you wanted a slope that was a different value, the idea is the same. You have a simultaneous set of equations. But what are your two equations? Your two equations will be the original equation and dy dx equals whatever number you want. Right? In this case, I wanted dy dx equals 0. But what if you wanted dy dx equals 1 or dy dx equals 10? Right? You'd have a different equation here, obviously. But the idea is the same. You get two simultaneous equations that you have to solve. Okay, so those are our horizontal tangent lines, right? The horizontal tangent lines are y equals 2 and y equals negative 2. I didn't really need the x values because I was only asking for the horizontal tangent lines. So I probably would have solved for x instead, but it doesn't really matter. All right, now part B.